Thank you for the introduction. This is tutorial, so it will be very easy. I'll try to make it very easy. So I prepared about 50 slides based on this paper, which took me about 4 years to write, actually. Took 4 years, actually. I don't have to go through all the slides. So if you have a question, just ask me. I'm willing to engage you. And the core idea will be covered in 30 slides. So if I cover 30 slides, I'm basically done. So I have a lot of collaborators who help me. Most of them are basically neuroscientists or psychologists, psychology, etc., etc. Also, a lot of people, and also I have to thank the NIH and the NSF to helping us to do this problem. Now I'm going to state the actual problem statement we're going to study. We're going to only study one problem. Now, this is a connectivity matrix coming from, it's a basically dynamic connectivity matrix coming from actual our brain, it's whole brain, actually fMRI. Now, I'm going to explain this data in some detail, but from this connectivity matrix that's changing over time, we want to actually do some sort of the data reduction in such a way that we're going to make this into state, changing state. 1 to 3. You want to ask me why you want to do that? Well, that's how the people do in this area. And I actually don't like it, this idea. Converting this continuous data into this kind of the discrete state. But sometimes it makes things very easy to provide some interpretation. So, does this make sense? I don't know, actually. It's we can do a lot of discussion here, but so I'm going to focus on how many states you're going to obtain. Can you guess? It's a racing slab MRI, so it's our brain activity when you're doing nothing. How many states do you think that exist?
3.
When you do nothing?
3, just based on these figures.
There's a lot of this is a problem that has been studying almost a decade. Still people are publishing a paper. And the most common sense, the consensus would be 3 stages. Also, that's what I obtained. We use a main different methodology. Most of the time, I don't want to say 3 stages. To me, it's like a 2.5. 2.5 summate to 3. However, if you use a different model, you will end up with totally different answers, like a hidden Markov model that will give you like a 10 stages. Some people come up with 50 stages, depending on how you analyze it. So there's no common sense, no consensus on how many states there will be. But I think the literature is going toward the 3 states. That's my guess. And I'm going to try to explain why 3 states. It's just an open problem. You can publish a lot of paper out here. So it's a great problem to start with if you want to get into this area. Yeah.
Are you trying to determine the state of the entire matrix?
Yes.
Okay.
So, I mean, this is a very trivial, essentially algebraic problem if this is single time series. Time series into state, this is not an issue. The difficulty is this whole matrix into a state. So that problem itself is not very well defined in a sense that some state might have a state 2. I mean, some part of the connection might be state 2, but other part of the connection might be state 3. So it has to be somewhat locally adaptive. That will most likely give you better answers. But still, we want to conceptualize into a finite state. And the problem is that the people has been working on this problem 10 years. I mean, we have a model methodology. The problem is it's not a good biomarker. The state itself is not a good biomarker for anything. So it has essentially no clinical relevance so far. And my guess is that it's something to do with the methodology they're using. Most people use geometric methodology. I think possibly our group is possibly the first group to use topological method to do this test space estimation problem. That's why we are getting slightly different answers. So now let me introduce this data. I noticed that a lot of people here is working on a cellular level network, so you might see this. So I'm going to go over slowly. All these images, there are three different imaging modalities. P1, which is structure, function, and it's diffusion. It's basically measuring the direction of the water molecule. So all came from a single scanner, MRI scanner. So it's a very nice. It's coming out school, and this is from the MCW. This is where the first paper, Bendettini, wrote the first paper on the fMRI, actually. He's in the NIH now. So MRI scan looks like this. So you can actually see the P1 weighted. You can see the structure, and it's some anatomy. So this is gray matter here, and this is white matter. White matter is basically connection, neuronal fiber connection, connecting the gray matter to gray matter, basically. And this is fluid here. Now, important part of anatomy would be circles here. It's basically the belly region, and this would be the gyrus. It's a mountain region. Now, this is very important for our study, and I'll show you that the connectivity in this region and this region is quite different. So simply analyzing functional connectivity doesn't make much sense, actually. You have to combine fMRI with MRI, actually, in some sense. So now, our method will not detect any side effect or sex effect, basically. It's a topological method. Now, this is when we say this in a paper for the journal Neuroimage, a lot of reviewer complain, actually. And also my co-author even complained. What's the point of developing a method that cannot detect the sex effect? Brain network, do you believe that the male and female are different in terms of the brain network? Or different? Or same? I mean, the California is a politically correct state, right? So I have to say something very politically very correct. It's known scientific fact that there are sex differences in brain network, both structure and function. It's a fact. It's a biological fact, undisputed fact. However, our method will not detect that kind of sex effect. Why? I thought about this problem a long time. My only conclusion is that if there exists a sex effect, that's most likely not topological. It's most likely geometric. The strength, for example, if you have the male females, women usually have a much better connection across hemispheres, bilateral connection, more bilateral connection for females, and the males usually have a front and back with the occipital region. So that's why males are very visual. And so those kind of known facts. Now the thing is that my guess is that those differences, male-female differences, are most likely geometric, or the difference in the strength of the connectivity, which usually doesn't translate into the topological differences. If there's topological differences, that will be geometric difference. But if there's a geometric difference, that doesn't mean there will be a topological difference. It's another jump. So that's my guess. Unfortunately, not many people work on this problem yet. So I strongly urge you, if you're interested in this problem, applying a topological method to differentiate the sex effect actually. Now, this is the ABCD study where we use about more than 7,000 subjects. And because the scanner, it's a different scanner. Because of the different scanner, you are expect to have a different image quality, and you should usually detect, you should be able to detect the side effect actually, if you're using traditional methodology. But again, our method will not detect this. Actually, we went through a lot of the, this is actually unpublished result. Actually, half of the presentation is not published result actually, it's just still ongoing research. So I just want to show you that our method is very dumb methodology. It's very insensitive methodology. And how big the brain network is actually at the MRI scan level? Well, if you're using 3 millimeter, it's usually 1.5 Tesla. That will give you about 1.67 billion connections. And that's about 5 gigabytes of memory. Now, if you want to build the brain network at 1 millimeter resolution, that's 3 Tesla, and that's the usual resolution of the MRI. And usually, not often, fMRI is usually about 2 millimeter, but sometimes you can have 1 millimeter. That's like 90 billion connections and 700 gigabytes RAM memory. So it's basically trying to build a brain network, 300,000 by 300,000 connectivity matrix. How are you going to load that into computer? You immediately get into the computation bottleneck. So this is the book I wrote, but we actually, this is exactly the network in this where each voxel is a node here. Again, you already see how dense network is. So if you increase the network to this resolution, you're not going to see much detail. It's just the meaningless junk actually. So now to go through the next stage of the talk, we need just a little bit of detouring. Now, this is basically what you're seeing is that the circle region and let me see which one. This one is, this is the gyrus, and this is circus here. I call it the red and blue. And what you're here seeing is that the circle pattern, actually. Circle pattern, actually we flatten it on a plane. It's a subject 1, subject 2, after using a pre-circle package. They are slightly different here. Now, if you want to compare brain network from here to here, from somewhere to here, I need some correspondence. So we're going to do the nonlinear registration of matching this to this. Now, X method will fail this task because all the X method use is what we call diffeomorphic registration that assumes a continuity of the mapping. However, this circle pattern, they are topologically very different. So you need a different technology. So we actually use the optimal transport. Optimal transport is getting into the registration, brain image registration recently. So we use optimal transport to match it, obtain this kind of field. It's still ongoing research. We need to fine tune it. So eventually we can actually match this kind of circle pattern to circle pattern. We can do it at the voxel level resolution. And we did a lot of optimization, and we can do this in 1 second in a laptop actually. So this is about the 400 subset. So if you do this, we can actually reduce this kind of the variability significantly. And if you perform some, for example, 2 sample t-test and male-female differences without this kind of alignment of the pattern, you're not going to see much signal here. This is our methodology after alignment. So we know how to align circle pattern to circle pattern, gyral pattern to gyral pattern. And then we can load the connected information and compare them at the voxel level resolution. Then surprising result kicks in actually. Now this is DMRI. So what you're seeing is about 1 million 1 meter 5 tracks per subject. It did that. Now I cannot show you the 1 million 5 tracks per subject. It's a MATLAB visualization. MATLAB will essentially blow up. So I only shown 2% of the 1 million tracks, 20,000 tracks per subject, only for the visualization. But actual computation is done on the 1 million tracks. It's basically showing the connection, where which part of the brain is connected to which part structurally. So I know exactly. This is the gyrus. I know which node of the gyrus will be connected to which node of the either gyrus or sulcus at the voxel level resolution. I'm going to represent this circle curves, gyral curves as a graph, three-dimensional graph. And I'm going to count on the fiber connection, number of fibers within the 2 millimeter resolution. Now, this is unpublished result. Then we get this kind of surprising result is that this is a circus. And so, well, you actually have a more dense connection in the mountain region of the brain compared to circle region. This is a known result in the literature. I just want to reconfirm it. So we actually reconfirm it. So there's nothing new. I don't think I can even publish this in a good journal because everybody knows it. It's a fact. So structural connectivity differs between whether it's in a mountain region of brain or valley region of brain. Now this is a resonance fMRI now. I'm going to show it every 30 seconds. You see the change here? See? It's very stable. At each point, at each pixel, it's fluctuating like crazy. This is actual fMRI at each pixel. It's going ups and down, okay, really crazy. But still, it's very stable spatially. That's the usual character of resonant fMRI. Resonant fMRI has to be related to the anatomy. Simply analyzing the resonant fMRI functionally, I don't think it's that meaningful. We have to correlate with the anatomy. So this is example. Now, eventually, with the resonant fMRI, we can actually we can construct gigantic correlation matrix, which is basically correlation is basically it's Pearson correlation. It's basically inner product of so it's like angle of the theta vectors, or what they call cosine angle in computer science. And in this network, you can see how many cycles are there. If this network has 300,000 nodes, how many cycles will be? Approximately this number of cycles. So that's our data. Now this is actually too much information. That's way too much information. Most people are not going to analyze at this level of resolution. So we need to parcellate this into some small regions like hippocampus, amygdala. And if you do that, it will be about, usually I use about 116 parcellation, and reduce it into 116 by 116 connectivity matrix. We just average whatever inside this parcellation and simply call it computer correlation. That's what a lot of people do. This is actually what you're seeing here is the resonant fMRI. This is what you're seeing here is the structural connectivity. Actual pathways of which part of brain is connected to which part. I simply superimpose connectivity made functional to the structure to see the pattern actually, the functional pattern. As you can see, you cannot figure out what's what here. This is the red is correlation 1, blue is the basically correlation -1. Yeah. But you can see that they are usually clustered. Huh? The question is where this high correlation will be clustered. Where? Huh? I'll show you the answer soon. Another characteristic of the resonant fMRI is that most of the connectivity is basically this part here, partial correlation. There are not many parts of the brain connection that show the negative correlation. It's very small. If you look at it, that's small. So if you look at the literature, most literature will simply ignore negative correlation and just analyze positive correlation. So negative correlation is a bit difficult to interpret biologically. So it's an example. Now this is also known result in literature. The difference is that the literature is not reporting this strong result. They know that the people who did this multimodal study knows that the resting state fMRI is very strong in this mountain region of the brain. But that's it. That's the current understanding. Now, if you go through all the routines, the way I explain it, you get the correlation. It's a within region correlation. It's a 0.98 between the mountain region and 0.97 in the belt region. Now, cross correlation between the circle and gyral region is 0.0027. That means it's a total, complete functional segregation. I'm not even doing clustering. It's simply cluster into two parts. Circle region, belt region, mountain region. Now, this kind of the information is currently not used in the brain network modeling yet. So I'm giving homage. I'm just distributing amazing good research idea actually here.
So what is the actual quantity along the x-axis?
It's correlation. It's correlation value. You will be surprised. I was so surprised that how can I possibly get this kind of strong, it's a really high correlation. I was surprised, did I make a mistake? So I went through code multiple times. I don't think I made a mistake. But this is from the HCP data set. It's a public domain data set. The one possible, it is possible I made a mistake somewhere along the line of 5.9. If there's a systematic error, you can have this kind of high correlation. But I don't think so. I have another data set, so I'm gonna reconfirm whether this is correct or not. And I think this is most likely correct one. Yeah. And I just want to show you. I got this result like a month ago, and I just want to see why there will be 3 stages. My guess is that, as you can see, this is one component. This is another component. Then there in the brain, there are region of brain that's not the mountain or belt region. It's somewhere. So eventually, my guess is brain network, brain region can be completely split into 3 parts. Mountain region, belt region, somewhere in the middle. 3 components, where the one region of the brain has a high connectivity, both function and structure, and less so. And what will happen is that in this kind of brain is a closed system. where you have in a network, you have a lot of the connectivity, less connectivity, and somewhere in the middle intermediate, then it will, my guess is it will form some sort of the reaction diffusion system. It will then eventually fluctuate like this. I have to prove that. Yeah.
Sorry, I'm still confused. I mean, in the images you showed us before, you had correlations that went from -1 to 1. And
Yes,
seemed to be
yes,
filling out that whole range. So what is it that's concentrated where all the correlations?
Oh, I'm actually correlating between. So, no. This is just the actually, this is the, I actually showed here. I think this might
The
be.
matrix of correlations.
Yeah. I think I should show from here. What I actually compute here is that there will be fMRI signal at each voxel. There will be fMRI signal. I'm going to collect this fMRI signal somewhere here to fMRI signal somewhere here. I'm going to do that.
And that's what's giving you the scores of 0.98.
That crazily high correlation, yes. Now, why no one ever done this? Because actually no one actually done this. It's a this is basically, to do this study, you need to use 3 modalities. Resonant fMRI, diffusion, and MRI. 3 modalities. It's 3 times more effort. So there was actually currently no study. The only study is a very limited study where they actually identify some circle region, not as a curve or graph, but some chunk of the region, and collecting this chunk of the region to another chunk of the region. That kind of the very crude computation. So that's why the literature is not reporting this strong result. That's my guess. Are you okay on this problem?
Am I working on this problem?
Yeah. No? Oh, I think it's an amazingly good problem. But it takes 3 times more effort. I'm serious. You need to worry about the 3 modalities. You have to, so you need 3 times more manpower, basically. So I have to thank NIH for helping me on this. So I just, this is a total mystery to me. I'm still working on this, trying to validate. I just need an independent data set. And if I duplicate in an independent data set, I'm done. And because of this 3 component, 2 component, 3 component, I think that's what is driving this fluctuation in the resonant fMRI. I know there's a lot of the paper trying to explain why resonant fMRI fluctuate. There's a lot of paper. Some people actually trying to explain neuronal level all the way to the voxel level. Yeah.
So would the result be different, or the number of states be different if you were using electrophysiology instead of fMRI?
You mean EEG?
Yeah, let's say.
EEG. I mean, you can do, but the problem is how are you going to put a node along the circle region? EEG spatial resolution is very low. I don't know. Circle spatial resolution EEG would be like what? 2 centimeter? I don't think you can put this EEG node within 2 millimeter. Can you? I have no idea. I don't think that's. No, this. And theoretically, you can do, but if you are willing to sacrifice a monkey, I think you can do it on a monkey along the circle region. I don't think you can do this with human. No, I don't think so. The problem is the spatial resolution of EEG. That's way too crude to do this kind of analysis. Yeah, it's fMRI specific, I would say. So I actually did some code and the data. If you want to play with it, you can just play with it. Now, what I explained so far is trying to do brain connectivity analysis without any kind of parcellation at the voxel level resolution. That's a lot of computation, a lot of things to worry about. So what the people usually do is they partially break into this kind of the known regions and average the fMRI signal here and simply correlate it. This is a known. This is what also our group also do. So this is an example of fMRI time series average into 116 brain region. Still crazily noisy. Resting fMRI is, if you look at the temporally, I would say that's like a 99% noisy, only 1% signal, I think. However, if you look at it more casually, also spatially, they are very homogeneous actually in some sense actually. So this is an example of a 400 subject. Now, my goal is analyzing this. What I just so far shown is this differential functional connectivity in a circle and the gyral region is trying to explain why we get this kind of three state, the underlying region. Now, I'm going to come back to the main story of this tutorial. I'm going to show you how to analyze this connectivity matrix. I'm sure you have even you can have a molecular network, and you can have this kind of the connectivity matrix. Then how are we going to analyze this? Well, the first obvious approach is to use a graph theory. You don't want to use graph theory. I'm serious here. For analyzing brain network, you seriously do not want to use graph theories. The problem is that it's okay. I mean, it's very intuitive, like clustering coefficient, like Q modularity, very physically easy to understand. The problem with it is applying those kind of graph theory features into weighted graph. Most of the graph theory features are developed on a binary network, 0 and 1. It's not developed for the weighted graph. Obviously, there's some weighted version, but those are very limited. The majority of the graph theory features are applied when the edge weights are 0 and 1. So it is necessary to threshold the connectivity matrix and use the unthreshold part of the connectivity matrix to build the graph theory features. What's wrong with that? It may not be wrong if you're analyzing on a single connectivity matrix, but brain imaging study at the macroscopic level is essentially statistical. We have like 400 subjects, 700 subjects. We have to integrate them across a subject. That means statistical analysis is critical. And if where you threshold it, you can actually end up with totally different conclusion. This is autism and the pediatric control. Now, depending on where you threshold, the small worldness will change. So you end up with totally different conclusion. We want to use it. It's a total nonsense. So I will never use graph theory. I think we never published any paper on graph theory actually. We got into this brain network analysis in 2009. From the day one, we used the Partial homology, topological data analysis. Why? Because this issue. I realized that when I get to this area, well, basically I was trying to write a grant, so I didn't know anything about the brain network analysis. I read a lot on that most people are using graph theory. Then I immediately realized that this issue. So that moment we decided not to use it. Then we are looking for tools. What tool to use for analyzing brain network? What tool will not have this problem? Well, obviously you need to have some multi-scale approaches, multi-filtration approach. So instead of thresholding brain network at some certain threshold, why don't we not to threshold it? Or equivalent is saying is that why don't we threshold every parcel threshold? Every parcel we're going to threshold it. Then you get information here, information here. They integrate them together. That's what the topology data analysis does. Eh? Topology data analysis is end game to the graph theory. Eh? So as far as you know, all the graph theory people in network science right now is going to a topology data analysis. Eh? When I met Mason, I met him when a long time ago in South Korea. Before he was doing a topology data analysis, when he was in the Cambridge University, he came to South Korea and presented his network. I think it was a multi-layer network. He was wearing pajama actually, giving a lecture. Everyone was totally shocked. Who give a presentation with pajama? Actually, but that gave a very good impression actually. A lot of people actually. Anyway. So a lot of for example, Daniel Bessel is not here, but her group originally didn't do the topology data analysis. But now they're also doing topology data analysis. So to me, topology data analysis is the end more like end game of the old graph theory. So, if you're not doing topology data analysis and doing graph theory, I strongly suggest you assign a student to do the topology data analysis. So, the why topology? It's totally data driven. There's no model. I'm actually cheating here. There's actual model. There's no such thing as no model. Whatever even I claim to be no model, that will be a model. Even K-means crossing doesn't have a model, but still that itself is a model. So what I'm saying is that no explicit model, like an equation. Also, we don't have to assume any kind of the distribution assumption. So it's completely data driven. So it's much easier. So I got into this area, topology data analysis, in 2009. It's a paper with Peter Bubeny and Peter Kim. I learned this topology from Peter Kim. He was a statistics professor who has an understanding of the algebraic topology, the layer combination. And we wrote a paper before Peter Bubeny was actually, he's very famous now, but before he was famous actually. This is actually the first TDA paper in brain imaging. So this paper, right now, if I'm looking back, it's not a very well written paper. It's written when I was assistant professor. It's not a good paper, but because it's a first paper, we did a lot of things for the first time that actually had a lot of impact to this actually had the first statistical analysis actually. Before this paper, no one knew how to even do the statistical analysis. So at that time, where this paper was packaged, exploited data analysis. Now I believe it's a total quantitative tool. I believe it. Because a lot of people worked on this. So then the next year, we actually were able to write this is actually first TDA paper in a brain network. I think most likely it is actually. Actually, I wrote another one, but that's just garbage. I don't want to even mention it. So this is the project I did when I was a Seoul National University in South Korea. I got actually big funding from the Korean government there. So I was a faculty there for 3 years. And that's why I met this amazing postdoc, Lee. So with Lee, we wrote so many papers, so many TDA papers. That's very nice actually. So this is...
Question?
Yeah.
So some time ago, I tried to learn about persistent topology as a tool for analyzing the neural recordings taken by people I collaborate with. These are electrodes, so this records activity of specific neurons in different areas.
Oh, it can be done, yeah. Yeah, it can be done. Yeah, we can do.
Okay, so, but I had a lot of difficulty difficulty understanding what the notion of connectivity, of connected parts of the graph, which is crucial to the persistent homology characterization of topology, would be interesting.
Oh, that's because
I am puzzled.
in the topology.
There is a famous anatomy called Valentino Breitenberg.
Oh, yes.
That if I start in a neuron in the cortex and I walk around from neuron to neuron until I come back to the neuron I started from, typically I will need 4 steps. So within 4 steps, every neuron allows me to create a loop in the brain. So within this information that we have about the anatomy for many years, why would I be interested in disconnected components?
Oh, actually, that's this is the first fundamental the topology is like a zero-dimensional topology. Connected component is zero-dimensional topology. Something that is connected or not is what we call zero-dimensional topology. Then you may ask, what's the first-dimensional topology? That's a cycle loop. Then you can go to the high dimension and you can build like a void. It's the cycle is like just a path, repeating set. Now the void would be something that involving like a base, etc. So you can build the dimensionality of this kind of the topological dimension. So that's why the connectedness is most important topology feature. I mean, all the graph theory features kind of topological feature. The problem is there's so many of them. But if you use this Partial homology, there are not many. Just connected component, cycle is what we call one cycle. Then the two cycle, 3 cycle, high dimensional cycle, etc. going. So that's all you need. All other topology feature you can derive from those, actually. And so I'm not sure whether I actually answered the question. The easy answer would be, suppose you have a one-dimensional signal. Then one-dimensional signal, like a timesheet, easy signal in a single channel. Then what would be the topology there? The only topology is you threshold it. Is something is connected or not connected? That's the only topology. So it's most fundamental topology. Then you cannot have this kind of loop structure. In one dimension, you cannot have a loop structure because it's basically interval. How are you going to form a loop? In order to form a loop, you need the additional dimension. So loop would be the next dimension. Then you increase the dimensionality. So it's more like a basis of this topological space, basically. So that's why it plays a very important role. And in this case, beta 0 would be counting number of connected components. It's like counting number basis, basically. So that's why. But I don't think I answered your question. I only answered your question mechanically. I don't think I answered your question very intuitively. But anyway, so if you want to do everything I'm talking here, I wrote the toolbox here. I was working with this toolbox with the postdoc, but the postdoc ran away. He doesn't want to do tool development. So I'm just working alone actually. I'm actually coding with the ChatGPT actually. ChatGPT is very good at coding. In some sense, actually better than postdoc. I'm serious here. I actually interviewed one postdoc last year and compared when I was doing interview, the interview process is like 1 month, 2 months. I keep asking a question. He gave answers. I compared the ChatGPT response to his question. See how many times he will come up with the answer I expect. It took like 10 times. ChatGPT about 3 times. So I didn't hire him actually. I'm serious here. So if you're not better than ChatGPT, you're not gonna get a job. You should be better than ChatGPT. So this is a toolbox I'm building with ChatGPT actually. So if you wanna help me, you can come to Madison and you can help me actually. But I have written about 7,000 custom library since 2 years. So we are building on top of the custom functions actually. So we can do everything whatever package Python has it. So I actually didn't even go through a lot of things, but this is all technical detail. You can go through this is what we call the graph filtration. So in order to go through this kind of multi-scale approaches, we simply delete one edge at a time and look at the topology. And then that's it. That's the idea. From this simple idea, we do a lot of things. I want to show that you can even compute the Wasserstein distance. It's optimal transport between the Parcellation diagram. But in our case, it splits. Wasserstein is split because of that. And then a lot of things. I'm sure you don't need this kind of technical detail. One thing I want to show you that if you go through this our framework is based on a distance based. Wasserstein distance is topology distance between the networks. That's what we are using. Inside model, we are only using distance. And everything is derived from distance. That's what we do. Even the clustering, we don't have model, only the distance. And then we can actually, within our framework, we can show that the topology inference is actually equivalent to the topology clustering. And convergence, local convergence, I actually demonstrated in a pro here, etc. And one thing I want to show you that this kind of, if you follow our framework, you cannot do this with the Lips filtration because Lips filtration, it combines the both and that in a very unintuitive way. But if you use our approaches, it will split. Both and that will split into this. So you can have this kind of embedding technology. It's still ongoing research. It's what we call both and that embedding, where we can actually, each node is basically a network. So in this case, I'm showing that there's no topology difference between male and female. It's a central here. You're not seeing it. But, this is a stupid method, you might say. No, it's not a stupid. We apply this to another tech data, temporal lobe epilepsy. In this case, it will split. It's a temporal lobe epilepsy, normal control. Okay, so in this case, the separation is basically zero-dimensional topology. It's like a connected component is more important than the cycle. That's how we separating the groups. Then we can do the gradient, topology gradient. Now, this is it's still ongoing research. It's not published yet, but this is amazing research. I like it. I'm going to publish this one. This one, you can see that there are about 117 subjects. We split the subject into 3 age groups and computed basically the embedding. Now, if you do embedding, you can see that this is young, middle, old. You can see the gradient here. So we're going to call it topology gradient. What it means, as you get older, cycles are disappearing and you get more disconnected structure. So your networks are not communicating each other. That's the conclusion. So you can do all this. I already distribute the code. So if you want to do this, you can just feed your connected matrix to my toolbox, and it will simply give you this result. And this is so each state is a network here. So I actually be the same methodology, and this again, this is work in progress. You don't see any pattern there, right? Now in this embedding we are developing, I'm actually seeing a pattern, crossing pattern. It's surprising. I'm not doing it. So it's like this is one state, another state, state. Now then, after doing this, I realized that it may be much better if you have a 3 states. It may be much better if you have additional dimension, 3 dimension. So each dimension would be the state. Then I think I can present this much better. Huh? It's just something. I'm done. You don't need to worry about this genetics. Actually, we also did a lot of genetic study. So this is our University of Wisconsin Madison. This is not our current campus. It's we still have snow now. So thank you. That's